Pre-calc. Now we're going to do exponential and log equations. This is going to be part 2. So really, last video, part 1, was all about exponential equations. Today is going to be all about logarithmic equations. So first piece, we're going to have two ways to solve it. You just saw we're going to have definition of logs, which we actually used when we talked about exponential equations as well. And then we're going to have what's called the one-to-one property. First step with definition of logs is you need to get the logarithmic expression by itself on one side. And then you're going to need to change into exponential form. Okay, now we're going to need to be careful on all these. After that, then once it's in exponential form, you should have the variable by itself. You're going to solve and then make sure you check your solution. Okay, that's going to be really important when we talk about logarithmic equations. Because remember, in the past we said we cannot take the log of a negative number nor zero. So all of our solutions, when we plug them back in, have to create a log of a positive number. That doesn't mean the solution has to be positive, just that it creates the log of a positive number. So a couple examples here. You'll see that our logarithmic expression is already by itself here. So I'm just going to change it into logarithmic form. So we have our base is 4, our exponent is 2, and therefore it equals what we're trying to take the log of. Now, solving this, we get 16 equals x plus 3. Subtract 3 from both sides, and we get that x is equal to 13. And here we would check. So what we're going to do to check, if I can get this, there we go. I'm going to take that 13, plug it back in. I have log base 4 of 16, and this is positive, so we're good. Okay, that's the big part about checking. Now, on this other one, there are a couple different ways we could solve this. We could apply the power rule and say that the natural log of 2x to the third equals 12. Or, and this is probably going to be the slightly easier way you'll see, we can isolate this log expression by dividing both sides by 3. So 12 divided by 3 is going to give us 4. Okay, and you'll see when we solve that this way is probably going to be a lot easier. So if I put this into exponential form, I'm going to have my base of e to the 12th power equals 2x to the third. And then to solve this, we need to get rid of the cube here. So we're going to take the cube root of both sides, which would leave me with just 2x here. And if I take the cube root of this side, remember a cube root is really 1/3. So this is like saying e to the 12 over 3. And 12 over 3 is going to give us e to the 4th. And then we divide by 2, and so x is going to give us e to the 4th over 2. Okay, likewise, if we did it the other way here, it would actually be it's the same amount of steps, but it would be one step shorter once we create our log equation, or exponential equation. So our base of e to the 4, our exponent, is going to equal 2x. And you'll see now we don't have to get rid of that cube root. So by dividing by 3, we don't have to worry about taking a root of something, which probably simplifies things a little bit for us. Now if we divide by 2, we're going to get e to the 4th over 2. And you'll notice they got the same result. So if we check this, if we plug this back in, we would have 3 ln of 2 times e to the 4th over 2. And since there's no negative signs in here, these are all going to be positive numbers. So we're okay. The 2's would cancel out, and the ln of e to the 4th is 4. And so 3 times 4 would give us 12, and we all work out. So then the one-to-one property, it's just going to tell us, it's a lot like our exponential one-to-one property, even if we didn't call it that. As long as the bases are the same here. So if log base b of m equals log base b of n, again, important that our bases are the same, then we can just say that m equals m. So it's a lot like when we had our exponential property that said as long as our bases were the same here, we can just drop our bases and say m equals n. Same idea. As long as our log bases are the same, we just drop them, and whatever we're taking the log of is what we solve. So first idea is that we need to write each side as a same base log, and the coefficients need to be 1. So if your coefficients aren't 1, that means you're going to have to apply the power rule and bring that in as an exponent. Then you apply the one-to-one property, which we just talked about, and finally you're going to solve, and again, really important to check the solution. So to show you an example of one that is really important to check the solution, like we said, we need to write it as the same log on both sides. So this problem looks a little more complicated than we've done before, and this one is going to be a little bit more complicated. It is going to create a quadratic equation, which you'll see in a minute. First thing we need to remember, to create one, subtraction is division when we talk about logs. So we need to take the log of x plus 2 over 4x plus 3 equals the natural log of 1 over x. Okay, so we have now used that whole MADS PM rule, the division is subtraction piece, to create one log on each side. And now since the natural log has the same base on both sides, we can just drop those. So x plus 2 over 4x plus 3 equals 1 over x. And here, this looks pretty complicated for us, and it is more difficult probably than we've done recently, but it's not too bad if we think about cross multiplication. So I'm going to multiply those two things. I'm going to get x times x plus 2, and that's going to just equal 4x plus 3 when I multiply 4x plus 3 times 1. Distributing my x now, I'd have x squared plus 2x equals 4x plus 3. And now I have a quadratic equation. To solve a quadratic equation, we've gone over several different ways to do that in the past, but initially you need to get everything on the same side first. So I'm going to subtract 4x from both sides, which is going to give me x squared minus 2x, and subtract 3 from both sides so that I have it set equal to 0. Here you can do two different things. You can use your calculator to do the quadratic formula, or you could factor this. If we factored, we get x minus 3 and x plus 1 equals 0. And solving those two equations, we'd end up with x equals 3 makes that one 0, or x equals negative 1 makes the second one 0. Okay, and this is an example of why it's important to check. Now, just because this is negative doesn't mean it's a problem. What means it's a problem is what happens when we plug these numbers in. So if I were to take 3, and plug it back into this original equation, I'd get the natural log of 5 minus the natural log plugging 3 in here. I'd get 15 equals the natural log of 1 over 3, which each one of these numbers is positive, so we're okay. No problems there. We'd simplify that. It'd be the same thing on both sides. If I plug in negative 1, though, I'm going to get the natural log of 1. That's okay. Minus, here's where we get a problem. The natural log, if I plug negative 1 in here, I'd end up with negative 1. And even on the other side, the natural log of 1 over negative 1 is negative 1. So this one's okay, but right here, we can't do that because they are a negative number. So that tells us that both of those solutions that we got are not actually solutions, and the only solution to this equation is x equals 3. Okay, so when it's we need to make sure we check by plugging in negative numbers, and when we decide when to use each one. Definition of logs is probably going to be easier to use when you have logs on one side already. Okay, and really we're going to be able to use either one of these pretty much all the time. But when we already have all the logs on one side, it's probably easier to use definition of logs. And when to use the one-to-one property is when we have logs on both sides. Okay, now both of these are important that we have logs with the same base. Otherwise, on the second one-to-one property, when we have logs with the same base. So that is it for this one. We've gone over two types, and using definition of logs is essentially the same as the exponential equations using definition of logs. We just changed the order. Instead of going from exponential to log form, we're going from log form to exponential form. All right, so we'll see you next time. Remember, really important that we check our solutions with these two.